Imagine the universe as this like grand cosmic ballet
Yeah.
with, intricate choreography and delicate balance.
Oh, yeah.
But instead of dancers, we have these fundamental forces that kind of dictate the steps,
Right.
ensure that everything moves in perfect harmony.
Yeah.
Without them, the whole performance would descend into utter chaos.
Wow, what a captivating way to put it. And it's surprisingly accurate.
Yeah.
These forces truly are the unsung heroes of the cosmos.
Yeah.
They're not just, shaping those grand waltzes of galaxies and stars,
Right.
but they're influencing the very atoms that make up our bodies and even the technology we use every day.
Absolutely. Welcome to Cosmos in a Pod.
Nice.
Space and Astronomy series. Today we're diving deep into the captivating world of these four fundamental forces of the universe.
Yeah, it's a journey that will take us from the familiar pull of gravity to the mind-boggling realm of the strong and weak nuclear forces.
Right.
Along the way, we'll uncover how these forces intertwine in a delicate cosmic dance,
Yeah.
orchestrating the very fabric of existence.
I'm ready to be wowed. But before we leap into the cosmic ballet,
Yeah,
could you give us a quick overview of these four fundamental forces?
of course.
A little sneak peek behind the curtain, so to speak.
So let's start with the one we all know and love, gravity.
Right?
It's the force that keeps us grounded, quite literally. It's what governs the orbits of planets around the sun.
Yeah.
A bit like an invisible string guiding their celestial waltz.
Right.
And on a grander scale, it shapes the large-scale structure of the universe, pulling galaxies together in a cosmic web.
Right.
Though it's the weakest of the four forces, its influence stretches across vast distances.
Yeah. Gravity for you, always working behind the scenes. What about the force that literally lights up our world? Electromagnetism, right?
Exactly. Electromagnetism is the force behind light, electricity, magnetism.
Right.
All the things that power our lives.
Yeah.
It governs the interactions between charged particles, which, let's face it, is pretty much everything around us. Without it, we wouldn't have atoms, molecules, or, well, anything, really.
Wow.
It's like the electrician of the universe, keeping everything running smoothly.
So gravity is like the choreographer, and electromagnetism is the electrician, making sure the lights stay on for the show.
I like that analogy.
But now we're entering a realm that sounds a bit more, well, intense. What about those nuclear forces?
Ah, yes, the nuclear forces. Let's tackle the weak nuclear force first.
Okay.
It's a bit of a behind-the-scenes player operating over incredibly short distances.
Right.
But its role is vital. Think of radioactive decay. The process is happening inside stars.
Yeah.
That's the weak force at work. It's like the stage manager,
Okay.
ensuring everything runs smoothly and on cue.
So it's like the weak force is making sure the set changes happen on time and the stars shine as they should.
Yes.
And then we have the strong nuclear force.
Right.
Is this the one that basically holds the entire universe together?
That's the one. The strong nuclear force is the powerhouse of the group.
Okay.
The strongest of the four. It's what binds protons and neutrons together in the nucleus of an atom.
Yeah.
Without matter as we know it wouldn't exist. It's like the super glue of the universe.
Wow.
Holding the very building blocks of everything together.
Okay, so we have these four forces, each with its unique role to play. But I'm guessing they don't just exist in isolation, right?
You got it.
They probably interact and influence each other in some way.
You're absolutely right. It's not a solo performance, it's a grand ensemble. And that interplay is where things get truly fascinating.
Okay.
For instance, imagine a cosmic tug of war between gravity, which wants to pull everything together, and the expansion of the universe driven by this mysterious force called dark energy, which is pushing everything apart. This cosmic battle will ultimately decide the fate of the universe.
Wow.
Whether it ends in a grand finale known as the Big Freeze, a dramatic collapse called the Big Crunch, or something else entirely.
So the fate of the universe hangs in the balance between these forces.
It does.
It's like a cosmic drama unfolding on a grand scale.
Yeah.
But what about the other forces? How do they contribute to this cosmic performance?
Well, let's take the electromagnetic and strong forces.
Okay.
They work together in a beautiful partnership. The electromagnetic force shapes the atom,
Right.
while the strong force ensures the nucleus remains stable.
Okay.
It's like a perfectly choreographed dance enabling the existence of atoms and the chemistry of life as we know it.
Wow.
Without this delicate balance, the universe would be a completely different stage altogether.
So they work together like a pair of dancers, perfectly in sync.
Yeah.
It's mind-blowing how these forces are intertwined at every level,
Right.
from the vastness of space to the tiniest particles. But I have to ask, what about the weak force?
Yeah.
What's its role in this grand cosmic ballet?
The weak force, though subtle in its influence, plays a critical role. Think about the stars. Those celestial furnaces burning bright in the cosmic night.
Yeah.
They're powered by nuclear fusion, the process of smashing atoms together to create heavier elements. And guess what?
What? The weak force is responsible for regulating that very process. Wow. It ensures a steady energy output from the stars, allowing for stable planetary systems like our own to exist and thrive. So the weak force is like the conductor, ensuring the orchestra of the cosmos plays in harmony, allowing for life to flourish on planets like ours. That's incredible. But I have a feeling we've only scratched the surface of this cosmic ballet.
You were right.
There's got to be more to the story, right?
You're absolutely right. What we've discussed so far is just the opening act to truly understand the universe's grand performance. We need to delve into the mysteries of dark matter and dark energy.
Okay.
They're like the hidden stagehands shaping the cosmos in ways we're still trying to understand.
Now we're getting into the really mysterious stuff.
Yeah.
I know these are some of the biggest enigmas in astrophysics right now. So what can you tell us about these shadowy forces shaping the universe from behind the scenes?
Let's start with dark matter.
Okay.
It's called dark because it doesn't interact with light, making it invisible to our telescopes. But we know it's there because of its gravitational pull. It plays a crucial role in galaxy formation and structure, holding them together despite their rapid rotations.
So we can't see it, but we can feel its effects through its gravitational influence. That's pretty spooky. And what about dark energy? Is that even stranger?
Even stranger indeed, dark energy is thought to be the force driving the accelerated expansion of the universe.
Okay.
It's like an anti-gravity force counteracting the pull of gravity on a cosmic scale. We don't know much about it, but its impact is enormous. It's essentially dictating the universe's future, writing the final act of the cosmic play. So we've talked about these individual forces and, their roles in this cosmic ballet.
Right.
But scientists are always searching for like a deeper understanding.
Yeah.
A grand unified theory that can explain all four forces.
Okay.
It's like trying to find the composer behind this intricate symphony,
Right.
The one who wrote the score for the entire universe.
The theory that explains everything, that sounds like a pretty ambitious goal. What are physicists thinking about, this grand idea?
Well, we do have the standard model of particle physics.
Right.
And it's been remarkably successful in explaining three of the forces.
Right.
Electromagnetism, the weak force, and the strong force.
Yeah.
But there's one notable absentee gravity.
Right.
That's the big puzzle, how to fit gravity into this framework.
Yeah.
And unify it with the other three forces.
So gravity is the rebel, the one that refuses to follow the rules.
You could say that it all comes down to the different ways we understand the universe.
Okay.
General relativity beautifully explains gravity on a large scale.
Right.
Planets, stars, galaxies.
Yeah.
But quantum mechanics reigns supreme in the subatomic world,
right,
where the other three forces hold sway. Reconciling these two theories has been one of the most daunting challenges in physics for decades.
Yeah.
It's like trying to merge two different styles of dance, each with its own rhythm and steps, into a single harmonious performance.
So we have these two theories, each brilliant in its own domain, but they just don't seem to want to dance together. Are there any promising contenders for this grand unified theory?
There are a few intriguing possibilities.
Like what?
Have you ever heard of string theory?
String theory?
Yeah.
I think I've seen that in a sci-fi movie or two.
Yeah.
Does it involve the universe being made up of these tiny vibrating strings?
You got it. String theory proposes that the fundamental building blocks of the universe aren't point-like particles.
Okay.
But these tiny vibrating strings, think of it like a cosmic violin.
Okay.
Where each string vibrates at a different frequency, creating different notes.
Uh-huh.
In string theory, those notes represent the particles and forces we observe.
Wow.
It's a wild concept, but it's mathematically elegant and could potentially explain everything from the smallest subatomic particle to the largest structures in the universe.
So it's like each string is playing a different note in the cosmic orchestra.
Yeah.
And all these notes together create the symphony of the universe. That's amazing. Are there any other contenders in the running for this grand unifying theory?
There's another fascinating concept called loop quantum gravity.
Loop quantum gravity.
Instead of strings, this theory suggests that space and time themselves are quantized.
Okay.
Meaning they come in tiny, indivisible chunks, like pixels on a screen.
Oh, wow.
It's like saying the stage of the universe is not a smooth, continuous surface, but a grid made of tiny squares.
So instead of strings vibrating in space and time, loop, quantum gravity says that space and time themselves are made up of tiny loops. That's really pushing the boundaries of how we think about reality.
It is.
But these are all just theories, right? Are there any real-world observations that support these ideas?
That's the challenge with these grand unified theories.
Yeah.
They're incredibly complex and difficult to test experimentally.
Okay.
But that's the beauty of science. It's a constant process of exploration, testing, and refining our understanding.
Right.
And even if we don't have definitive proof yet, these theories offer tantalizing glimpses into the deeper workings of the universe.
So much to learn, so much to explore. It makes you realize how much we still don't know about the universe and its fundamental forces.
It does.
But speaking of exploration, I'm curious to see how these forces play out in the real world,
Right.
beyond the theoretical realm.
Absolutely. Let's shift our focus from the theoretical stage to the grand cosmic theater itself.
Coke.
We've talked about stars, those brilliant beacons of light scattered across the cosmos.
Yeah.
They're a prime example of the delicate balance between gravity and the other forces.
All right, let's talk stars. What's going on inside these fiery behemoths
Yeah.
that makes them shine so brightly?
Stars are born from vast clouds of gas and dust, mostly hydrogen and helium gravity. The ever-present choreographer pulls this material together, compressing it and heating it up. Eventually, the core of this collapsing cloud gets so hot and dense that nuclear fusion ignites.
Wow.
This is where the strong force takes center stage,
Okay.
binding hydrogen nuclei together to form helium, releasing a tremendous amount of energy in the process.
So gravity sets the stage, and then the strong force lights the fuse, so to speak.
Exactly. This fusion process creates an outward pressure that pushes against the relentless inward pull of gravity. It's this delicate balance that keeps a star stable, preventing it from collapsing under its own weight.
It's like a cosmic dance-off with gravity and the strong force locked in an epic battle. But what happens when the fuel for this fusion process runs out? Does the party just end?
That's where things get really interesting. A star's ultimate fate depends on its mass.
Okay.
Smaller stars, like our own sun, will eventually swell up into red giants and then gently shed their outer layers, leaving behind a dense, smoldering core called a white dwarf.
Right.
It's a quiet, graceful exit from the cosmic stage.
So a peaceful retirement for smaller stars, but what about the really massive ones? What happens when their fuel runs out?
Yeah.
I'm guessing things get a bit more dramatic.
You could say that when a massive star exhausts its nuclear fuel, it can no longer support itself against the relentless crush of gravity.
Yeah.
The core collapses in on itself and the outer layers are blasted away in a spectacular supernova explosion. It's like the grand finale of a cosmic fireworks display.
Supernovae. Those are incredibly powerful events, right? What happens to the core of the star after such a dramatic explosion?
The remnant of the core can become a neutron star, an incredibly dense object made almost entirely of neutrons.
Yeah.
Or even a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. It's like the stage collapses in on itself, creating a cosmic abyss.
Neutron stars and black holes. Those are some of the most extreme objects in the universe.
They are.
It's amazing how the interplay of these fundamental forces can lead to such dramatic outcomes.
Yeah.
But it's not just about stars, right?
No, it's not.
Planets, those celestial wanderers, also owe their existence to the delicate balance of forces.
Absolutely. Planets are held in their orbits by the intricate interplay between gravity and inertia.
Okay, so gravity is the force that keeps planets from flying off into the vastness of space. But what role does inertia play in this celestial dance?
Inertia is the tendency of an object to resist changes in its motion.
Okay.
It's like saying, I'm going to keep doing what I'm doing unless something forces me to change.
Right.
So while gravity is constantly pulling a planet towards its star,
Yeah.
the planet's inertia wants to keep it moving in a straight line. The result is a curved path in orbit.
Right.
Where gravity and inertia find a harmonious balance.
It's like a cosmic waltz with gravity leading and inertia following,
Yeah.
creating this beautiful elliptical dance around the star. And it's not just individual planets and stars that are influenced by these forces, right? Entire galaxies.
You got it.
Those sprawling cosmic cities of stars are also shaped by this interplay.
That's right. Galaxies are vast collections of stars, gas, dust, and that mysterious dark matter we talked about earlier.
Yeah.
All held together by gravity. But it's not just gravity that gives them their shapes and keeps them from flying apart.
Right.
Rotation also plays a crucial role, as does the elusive dark matter.
So gravity is the glue that holds galaxies together.
Yeah.
But rotation and dark matter are like the architects, shaping their structure and preventing them from collapsing in on themselves.
Exactly. Galaxies are like giant spinning disks, and this rotation creates an outward force
Okay.
that counteracts the inward pull of gravity, and dark matter, even though we can't see it, directly exerts a gravitational influence
Yeah.
that helps to hold galaxies together and shape their spiral arms.
It's mind-blowing to think about these forces operating on such a grand scale, shaping entire galaxies and influencing the evolution of the cosmos.
Yeah.
But what about the smaller scale? What about the forces at work inside atoms?
Right.
The building blocks of everything we see and touch.
Well, as we mentioned earlier, the strong nuclear force is what holds the nucleus of an atom together, binding protons and neutrons in a tight embrace. But there's also the electromagnetic force at play,
Right.
governing the interactions between the negatively charged electrons and the positively charged nucleus.
So the strong force keeps the nucleus from flying apart, and the electromagnetic force keeps the electrons in orbit around the nucleus. It's like a miniature solar system within each atom.
That's a great analogy. It's like a miniature solar system with the nucleus as the sun and the electrons as the planets, all held together by the electromagnetic force.
Right.
And just like with planets orbiting a star, there's a delicate balance
Yeah.
between the attractive force of the nucleus and the electron's inertia.
It's incredible to think that these same forces that shape galaxies and stars are also at work inside the tiniest particles governing the very structure of matter.
Yeah.
It really highlights the interconnectedness of the universe, how everything is ultimately governed by these fundamental laws.
You're right. The universe is a tapestry woven from these four fundamental forces.
Yeah.
And understanding their interplay is essential to unlocking the secrets of the cosmos. It's like deciphering the language of the universe, understanding the code that governs everything from the smallest particles to the largest structures.
It's been an incredible journey so far.
Yeah.
Exploring the fundamental forces and their impact on the universe at every scale. We've talked about gravity, electromagnetism, the strong and weak nuclear forces, and how their interplay shapes everything we see around us. But before we conclude our cosmic adventure, I think it's important to acknowledge the challenges and unanswered questions that still remain. You're right, even with all the amazing things that we've discovered, there's still so much we don't know.
Yeah.
Like, for example, the true nature of dark matter and dark energy continues to be one of the biggest puzzles in cosmology.
Yeah.
We know they exist, we can measure their influence,
Right.
but their true essence remains elusive.
It's like we're trying to complete a cosmic jigsaw puzzle,
Right.
but some of the most crucial pieces are missing.
Yeah. And then there's the ongoing challenge of uniting general relativity with quantum mechanics.
Right.
They're both pillars of modern physics.
Yeah.
But they seem to clash at a fundamental level.
They do.
We talked about string theory and loop quantum gravity earlier as potential theories of everything. Are those still the leading contenders in the quest to bridge this gap?
They are, but there are other exciting ideas emerging as well. The search for a unified theory is one of the most captivating and demanding areas of research in physics today.
It sounds like it.
It's like trying to find the universal language of the cosmos,
Right.
A language that speaks to both the grand sweep of gravity and the intricate dance of subatomic particles.
It's not just about theoretical puzzles either, right?
Yeah.
There's still so many observational mysteries out there that we're struggling to unravel.
Absolutely. Take black holes, for instance.
Okay.
They're among the most extreme objects in the universe, pushing our understanding of gravity to its limits. What happens at the singularity of a black hole,
Yeah.
where all that matter is squeezed into an infinitely small point?
Right.
It's a question that continues to baffle physicists.
It's like the ultimate cosmic riddle.
It is.
We know black holes exist. We can even witness their effects on their surroundings.
Right.
But what's happening inside them remains shrouded in mystery.
Yeah, and then there's the question of the universe's earliest moments, the first fleeting moments after the Big Bang.
Right.
We know the universe went through a period of rapid expansion called inflation,
Yeah.
but the driving force behind that remains an enigma.
So many questions, so much left to uncover. It can feel a bit overwhelming,
Yeah,
but it's also exhilarating.
it is.
It means there are still countless discoveries waiting to be made.
Right.
So much more to learn about the universe and our place within its grand design.
Precisely, the universe is an expansive and complex realm,
Yeah.
and we're just starting to glimpse its intricate wonders.
Right.
But each new discovery, every piece of insight we gain, brings us closer to understanding the intricate dance of the fundamental forces.
This has been an incredible deep dive.
It has.
Exploring these fundamental forces and their impact on the universe at every scale. From the smallest subatomic particles to the largest galactic structures, we've journeyed through the realms of gravity, electromagnetism, the strong and weak nuclear forces,
Yeah.
and witnessed how their interplay shapes the reality we experience.
Right.
We've also pondered some of the most profound, unanswered questions that continue to drive scientific inquiry.
Mm-hmm.
The nature of dark matter and dark energy, the quest for a unified theory, and the mysteries of black holes and the early universe.
Absolutely.
So much to ponder, so much to explore. If this deep dive has ignited your curiosity, we
Yeah.
encourage you to continue your exploration of the cosmos. There's a wealth of knowledge out there.
Right.
Books, articles, documentaries
Yeah,
that can take you on an even deeper journey through the wonders of the universe.
for sure.
And of course, we invite you to follow and subscribe to Cosmos in a Pod
Yes.
and our YouTube channel for more in-depth explorations of the fascinating world of space and astronomy. Thank you for joining us on this cosmic adventure. Until next time, keep looking up and never stop questioning the universe and its boundless mysteries.